And I'm very happy to announce that, in essence, phase one engineering for us is complete. What we have today is a much simpler circuit. We've replaced those double feed bins with a single silo, double the capacity. The idea behind that is we just reduce operational risk. We've replaced all of those complex float circuits with Jameson float cells, so there's 6 of them, which reduces the entire footprint of the plant dramatically. And I like data-driven decision-making. You don't make these decisions based on emotions. You've got to have hard facts that backs you up.
I'm thrilled to have with me today Highland Copper's Copperwood Project Director, Dr. Wynand Van Dyck, to discuss the completion of Phase 1 engineering, which has been completed at the project. Dr. Wynand, how are you today?
Doing really well. Thank you, Romeo, and always a pleasure being here.
Awesome. Now, here's how today's going to work. He's going to run through a presentation, then I'm going to ask a few select questions. We're going to get really into the technical details today. If you have any follow-up questions, as this will be a recording that you're watching, please do reach out, and I'll make sure that the Highland Copper team gets them, and we'll get back to you as soon as possible. Without further ado, Dr. Wynand, I'll pass it on to you.
Yeah, Romeo, as stated, thank you so much for the opportunity. Appreciate it as always. Great just being in a position of reporting on the phase one engineering and what's been done so far. A little bit just setting the context. We dove into this phase one in January 2025. That was announced, and we had two main goals. First of all, we wanted to make sure that we finalized design criteria before we get going in all earnest. And then the second piece is actually assessing opportunities of just improving the project. I have to acknowledge the team of people that worked with us. This certainly wasn't done in isolation. We had DRA Americas looking after the mine and the process plant engineering work. Both looked after the overall water balance, and we had Tetra Tech looking after the tailings disposal facility for us. And I'm very happy to announce that, in essence, phase one engineering for us is complete. So what are we going to talk to you about today? The objective of this webinar is we want to just discuss briefly the recap on the process plant, talk about some of the work done on the mine engineering and the tailings dam, give you some guidance on the pathway forward, and then certainly use the opportunity to just give the listeners an update on where we are from a site perspective and the work that's been done there. So let's talk about the process plant. First of all, good news is we've done the webinar, I think it was about 6 weeks ago. We got really technical about the process plant, so we're not going to go into that level of technical detail today. But I do want to just touch on the work that was done for those that's missed it and try and summarize all of that. Recapping what we had in 2023 in the feasibility study. We had this circuit was done on test work done by SGS, single milling circuit, SAG mill and ball mill, milling down to about 45 microns. 8 conventional roughers that concentrate fed a regrind mill. From that regrind mill, we had quite a complex cleaning circuit. There were 25 conventional trough cells in various configurations. All of that conc went into a concentrate thickener and filter, and there was no tailings thickener in this process. What we have today is a much simpler circuit. We've replaced those double feed bins with a single silo, double the capacity. The idea behind that is we just reduce operational risk. We've split the circuit, the milling circuit, now into what's called the MF2 circuit. So we've still got a SAG mill and ball mill right up front, but those are smaller. We are milling down to 80 microns on the front end rather than 45 microns. Primary rougher and a scalper circuit. We then de-slime and have got a secondary mill. Now, from a flow perspective, about 25% of your material goes into this rougher conc circuit. About 25% of the material goes over from a de-sliming perspective. That means only about 50% of the material are seeing the secondary mill. So we can mill down to 38 micron. So we've got a smaller millers up front, smaller secondary mill, regrind mill going down to about 10 micron. We've replaced all of those complex float circuits with Jameson float cells, so there's 6 of them, which reduces the entire footprint of the plant dramatically. We've installed a tailings thickener, or just decided on using a tail thickener, and what that gives us is that we can, in essence, recycle our water immediately back into the plant, and the thickened tails goes to the tailings dam facility. What all of this gives us at the end of the day, certainly higher recoveries and a lower cost. Previously, the baseline for the project was 86% recovery. We're now down to, or up to, almost 88. optimize the reagent scheme. That saves about $1 a ton on OPEX. There's also further OPEX savings in that it's about 1.5 megawatts of power that we will not draw, not just install, and we won't draw that power. And that gives you some additional power savings there. We've got a much smaller and certainly a much smarter flotation plant. That the good news is there, we've reduced and cut out a lot of the complexity. And then lastly, the other operational improvements like the silo, pump redundancy, having a PLC SCADA control system, all of that will just improve the reliability and align with what we've got currently in the area to work with. Pretty happy from a metallurgical perspective. I think we are ready to step into the detailed design from that perspective. Let's talk about the mine engineering side. Now, on the mine engineering side, DRA looked at several optimization efforts for us. And the first one was trading off on room and pillar versus drift and fall from a mining perspective. The 2023 feasibility study had room and pillar mining in. It's the current base case. It is a proven method, certainly nothing wrong with it. It was used historically at White Pine, so certainly for us, we do think it's a valid mining method for the ore body. And this is a little bit of a very simplified graphic of what it looks like. So you mine these drifts in a square pattern that creates these rooms, and there's some pillars that you leave behind. The drawback of room and pillar mining, especially if you're not roping the pillars, is that your overall mine recovery is, call it high 60s, maybe touching 70%. So DRA therefore evaluated drift and fall mining for us. Now, in drift and fall, we're now mining these much longer drifts. Once you've finished mining a drift, you come back and you pump it full of paste, and that paste is made out of your tails with call it cementatious binder. Once that is settled and you have the structural strength of the paste, you can then come back and now you can mine the area between these paste-filled areas, which is solid. So your paste becomes the roof support. Again, a oversimplified version of what happens. What this gives you, as you can imagine, it takes your mine recovery from, call it the 70% to the mid-90s. You use some of your tailings now underground, so that improves your tailings footprint and makes that smaller. It certainly reduces a lot of your geotechnical risk because your strength of keeping the roof up now comes from these drifts that's full of paste backfill. However, you will need a paste backfill plant. Now, in all of the work that was done by DRA, certainly it looks like a hybrid approach where in these western panels, we'll be using drift and fill, these ones marked in green, and then all the other panels will stay with the room and pillar mining method. And certainly that gives us, could enhance the project economics. We are very encouraged by this, but it is dependent on whether we can make a paste of sufficient strength. So that's something that we'll do very early now in phase 2, do some paste test work, and make sure that we can actually keep the roof up using those paste. And then once we have those results, we'll consider all of the merits, and then including environmental and permitting, before we actually make the decision to make this change. Other piece of work that the DRA did for us is they reviewed the excavation method or the mining equipment. 2023 feasibility study used road headers where we had the mine height above 3 meters, and conventional drill and blast using these 2-boom jumbos and mining height below 3 meters. And the 3-meter number is purely because the size of this piece of equipment. So what they reviewed is productivity assumptions associated with these road headers. And keep in mind, these are big machines. They're not overly maneuverable. How do you sequence that with the roof bolters coming in, and the overall impact on the cycle time? And where we are today, we'll continue to assess the technical and financial merits of using these road headers. Frankly, we'll look at the optionality of a phased introduction rather than going the whole hog right up front. And the whole idea behind this is just managing risk. What you don't want is having a plant that's commissioned, ready to run, but you cannot feed the plant. So that's certainly the optionality that we are looking at this point in time. From a tailings and water management perspective, 2023 feasibility study, as we mentioned previously, just pumped unthickened tailings to the tailings dam or the tailings disposal facility. What we are doing now is we're looking at putting in a tail thickener. So your percent solids goes up to around about the 50%. And immediately that reduces the size of the footprint. The other advantage is it allows us to recycle our water immediately back into the process plant. And you're not pumping the water all the way to a tailings dam where it can evaporate and then try and recover it from the tailings dam and back to the plant. So that cuts some water handling cost. And certainly because we're no longer using the tailings dam to store the contact water, that reduces instability risks substantially. Because you have a smaller footprint, that creates some space, and that space we'll use to then construct a permanent return water dam, or rainwater retention dam. That's this blue area in this graphical representation, the concept. I want to stress this is just a concept because it all depends on how much tailings you're going to store underground. But we've updated the water balance. We ran various climatic scenarios from extreme wet to extreme dry to make sure that we have enough space and we can actually keep the plant fed from a water perspective, and then we can manage the risk. So as part of phase 2, once we understand the volume of the tailings, then we can now look at optimizing the embankment designs. And obviously from a closure perspective, if you've got a smaller tailing footprint, optimize how do we close the facility down. One last piece of work that the DRA looked at for us is the option of just using the underground void as a storage facility for some of our tailings. Now, this is slightly different from the paste backfill. Yeah, we don't have it's still a paste thickened, but we don't have a binder. So in this case, we'll construct these, call it Brattis walls in the mined out areas, and then just take that paste and actually just pump it into the void. The study indicates that we can store almost 8 million cubic meters of thickened tailings underground. That reduces your tailings DDF footprint by about 40%, and that's real value for us. Again, this has to determine the ability, can we form a paste, and is that a reliable way of operating the plant? And that we'll test now early in phase 2. And once we have clarity on that, we'll assess that in the phase 2 engineering. So talking about phase 2 engineering and the pathway forward, just give you a brief glimpse of the current thinking and where we are. As mentioned, metallurgically, we're pretty happy with what we have from a design criteria perspective. But while we wanted to be in the same place on the mining method, certainly the work that's done to date suggests that we need a little bit more work. There's 2 key inputs. First of all is this paste test work that I've previously referred to. And that's going to take us about 3 months to do. And the only reason why we're starting now is the metallurgical test work is pretty much wrapping up. So we've actually got the tailings, the actual process tailings and the water that we can use to actually do this paste test work. And the second piece is labor cost. Just do an update on our labor cost. All of that, while we're waiting, we want to use the opportunity to actually do a review of the entire mine plan. Starting with ground support, mining height, mining equipment. Clearly, if you're doing a mechanical cutting of the ore versus drill and blast, you have less shock, the roof and ground support. So use this time that we have while we're waiting for the results of the paste test work to actually do an integrated review of the entire mine plan. And then depending on the final design criteria, then we have to make the call on what about permits and permit amendments. So if we need to do permit amendments, then obviously we will have to adjust the schedule accordingly. But we remain very encouraged. Recently, we have successfully amended some permits and on a timely basis. So we do believe that we can manage that risk. Once all of this work is done, early in the new year, we'll proceed into the phase 2 detail engineering, and then in parallel with permit amendments if needed. And certainly then be in the back end of 2026, support a construction decision and project financing. Lastly, let's talk briefly about the site update. Great pleasure to report that all the construction work is done. Our site team keeps on delivering. So all of the construction work that we had to do is behind us, done on schedule, on budget. We're busy with the paperwork, literally on as-built drawings. The concurrent reclamation work has also done a huge amount of effort there. We finished all our seeding and tree planting work, and we're actually now in survival warranty analysis. And these 2 photographs just at the top just shows you what's happened to the site. This is what it looked like in May on the gypsy wetlands that we built. That same wetland in August. The plant growth has now started, and this is exactly what we want to see. Pretty happy with that. Lastly, in terms of Bluff Creek, that's the work that we were doing offsite, where we replaced these undersized culverts with a clear span bridge. That work is also done, all the in-stream work is done, and we're busy with the as-built drawings on that. So we're now moving from a site work into the monitoring program, and pretty happy with where that stands. So so thank you for the time, and happy to take some questions as well.
Awesome. Appreciate it. I do have a couple questions that I was hoping to run through. As you said, we did that detailed webinar on the metallurgical circuit about 6 weeks ago. And I know that you mentioned you're doing that variability test work. I'm curious, beyond what you've shared already, is there anything you can talk about on the results of that test work today?
Yeah, good question. We didn't talk about it just from a timing perspective. Happy to say that most of the variability test work is now done, and the results certainly looks good. Gave us the same level of performance than what we had. We've even run lock cycle test on that variability test work, and we fall on the same grade recovery curve. So that gives us a lot of confidence on the metallurgical design, and that's why we're saying we're comfortable stepping into detailed design once we get the go ahead. But let's finish the work on the mining side before we step into the detailed design on the metallurgy side.
Okay, makes sense. I know the potential shift from room and pillar to that hybrid approach that incorporates drift and fill mining could increase recovery from, I think, 69% to 94%. So that's a really substantial difference. I know earlier studies must have looked at drift and fill. So what's changed now that you're viewing it as truly optional for the project?
Yeah, you're quite right. Earlier studies did look at drift and fill. What's changed, frankly? Copper price. You got to have, if you want to go drift and fill, it means you need a paste backfill plant, which is going to introduce additional capex. You also need sometimes a substantial amount of binder and or some form of aggregate or slag that you use to give you additional structural strength, and all of that introduces additional OPEX. So you got to be in a position where the revenue can offset this additional revenue that you get, can be offset by, and certainly pay for the capex and the OPEX. And what we've been seeing, the copper price has been hovering around the $5 mark. Certainly it's been stable from that perspective. And at a $4.50, it starts opening up the window of opportunity where drift and fill can be seriously evaluated. That's what's changed.
No, I appreciate it. That's a great answer. I know you're taking an integrated systems approach to mine design. So that's linking, ground support, excavation method, back height, tailings disposal. Can you just explain to the folks watching why this holistic view is important and what it means practically speaking for optimization of the project?
Yeah, if you look at systems theory, you cannot optimize a integrated system by optimizing the subsystems. You always end up with a suboptimal design. And unfortunately, in a large degree, we've locked very much into the subsystems and tried and driven the optimum approach there. But you have to look at this integrated. There's no argument about it. So what we're trying to achieve here is actually looking at just take a rethink. We have got the time. We're doing this paste test work. It's going to take us 2-3 months to get that done. Use the opportunity of actually take a overall review and look at this from an integrated system. Does what we want to do, does it all make sense? As you quite rightly say, all these building blocks are interrelated. So we want to be sure that we're not having little local optima, but that we have a global optima. And that approach and that way of thinking certainly returned the results on the metallurgical side of things. That was exactly what we did. And we're hoping to replicate the same thing when we get to the mining side.
Great. Now, I know that you previously had said that you want to progress the tailings disposal facility design to about 85%. Is that still the plan, and what's the progress towards that so far?
Yeah, that's certainly still the plan. Remember, although our tailings dam is permitted, our drawings has to be signed off as part of our dam safety permit. From a de-risking the critical path, we absolutely want to get as far as we can with the detailed design of the tailings dam. However, we got to have clarity on how much tailings are actually now going to be stored on the tailings dam. If we're going to use a paste backfill facility, or if we're storing tailings underground, or it's paste from a drift and fill, that influences the amount of material that's going to go onto the tailings dam. So we've paused the detailed design. All the design parameters, as much as we can, is done on the paste or on the tailings dam. But once we have the quantity numbers, then you can pull the trigger on running with the design on the tailings dam. So certainly still the plan. But once we finalize quantities, then we'll pull the trigger and go to that 85%.
Great. Now, what I'm going to throw one at you that kind of sums up, I think, a lot, and that's given you got 30 years of experience in metallurgical design, construction, operations. So asking you pretty straight, what aspects of the Copperwood project make you really confident in its potential to become a successful operating domestic copper mine?
I think one of the key strengths of Copperwood is just the amount of technical data that's out there. This project has been going for a while. There's been a lot of engineering work, a lot of test work done. And I like data-driven decision making. You don't make these decisions based on emotions. You've got to have hard facts that backs you up. And that for me is, maybe strength number one. Is just the amount of information that we have on making the decision from a design perspective. I think the second side of it is just integrating a risk-based approach from the word go. The design team certainly look at all the, call it the ilities, the operability, the maintainability, the constructability, all of those things we try and incorporate from the word go to make sure that you have, this is not just about delivering a project and that's on time and hit the budget and we all celebrate and walk away. And then from an operational perspective, we can't get this project commissioned. Driving the team right up front to considering that, I think is a strength. Using the time wisely, being very pedantic in the way that we step through from design criteria. And I think all of that is just good state. It's about managing the risk associated with the project.
Awesome. Dr. Wynand, thank you so much for running through both the presentation, but also letting me grill you on the technicals. I always appreciate your time. I think this was really helpful for viewers.
Romeo, as always, just appreciate the opportunity and great spending time with you and talking through. So, yeah, good stuff.
Awesome. Have a wonderful end of your afternoon.
Thank you.